Hi, this is Mahesh Morjaria. I'm EVP at Terabase Energy, responsible for operational technology. Prior to joining Terabase a few months back, I was with First Solar for about a decade. Today I'm going to address the topic of advances in frequency regulation from solar plants. A solar plant is a type of inverter-based resource, or IBR. The key message I want to leave you with is that solar plant provides energy, flexibility, and capacity. These are the three elements required for grid stability and reliability. First of all, utility scale PV solar can become a grid-friendly resource and contribute to grid stability and reliability like other resources. Secondly, utility scale PV solar also provides essential reliability services and grid flexibility that are normally provided by conventional resources. Finally, combined with storage, which makes it a hybrid plant, solar provides clean and competitive firm capacity. Next, I'll describe how PV plant supports grid reliability, which includes frequency regulation and flexibility. Grid-friendly solar IBR is now well established. What I mean by that, it has been amply demonstrated that PV plants provide the features required by NERC to be a good grid citizen. This includes voltage regulation, active power control, which includes ramping and curtailment capability. It also includes the ability to ride through grid disturbances and not tripping off. It should also provide primary frequency droop as well as short circuit duty control. So these are some of the features that represent the base capability of a grid-friendly IBR. A key enabler for achieving these grid-friendly features is a smart power plant controller. Its function is illustrated in this chart. It starts with measured grid conditions at POI, which include total active power output as well as voltage at POI, or point of interconnection. It compares those measurements with the desired set point provided by the grid operator or the plant operator through the SCADA system. It then sends individual instructions to each inverter based on its location, performance, and losses to change its output in a closed loop fashion so that the POI set points are achieved. It acts like an orchestra conductor, ensuring that the quality of power output of the entire plant is as required. The closed loop acts at every 100 millisecond loop, and hence the overall plant performance is very responsive. Next, I'll show you an example of how solar plant provides essential reliability services. These include frequency control as well as various other services that NERC has defined. This was a project that was undertaken in collaboration with California ISO, NREL, and First Solar. We took a 300 megawatt PV plant that First Solar had developed to illustrate this capability. We then estimated the available power from the PV plant as shown by the green line in this figure. Next, we left 30 megawatt headroom. It was just an example, an arbitrary number, within which CAISO can regulate the power to control the frequency on the grid. This is kind of illustrated next. The means of controlling the frequency by CAISO was to send an AGC, or automated generation control signal, every 4 seconds. This is illustrated by the blue commanded megawatt line. The response of the PV plant is shown next. As you can see, the solar plant regulation accuracy was very high. As you can gather from this figure, it was closely following the commanded megawatt signal. It is a remarkable result, and in fact, it was found to be 27 percentage points more accurate than if the fastest conventional generation, typically a gas turbine. It is a remarkable results achieved principally because of the power electronics utilized in the solar plant. The effort won numerous awards. We demonstrated that the PV plant can also provide other services like up regulation, down regulation, frequency regulation is yet another form, and flexibility in this particular study. Next, I'm going to show you an example from that demonstration on frequency Droop test. Here on the right figure, you can observe that the frequency drops beyond the dead band of that set for the PV plant, and the PV plant increases power output very fast, and then as the grid frequency recovers, it goes back to the pre-disturbance normal power. For the plant to increase its output, it needs to have some reserve power available, as is also the case for a conventional generation. Here is an example from an over-frequency Droop test. You can observe that as the frequency increases, shown on the white graph, the power output of the plant decreases corresponding to the frequency increase. This is when the frequency goes beyond the dead band. And it recovers back to the pre-disturbance normal power when the grid frequency returns within the dead band. And some measurements were taken for the Droop response both at 5% as well as 3%, and it behaved extremely well. We recently had a successful commercialization introduction of AGC capability that I mentioned before. This was in Chile. What you see here is an example where instead of selling energy at a low price, in this case it was $12 per megawatt hour, the plant was able to bid into the market, a day-ahead market, at $32 per megawatt hour, and the bid was accepted. And what you are seeing on the right hand side on the figure circle particularly is the blue trace, which shows how the plant was exercised in order by the grid operator for this service, which was put in commercial practice as well. Now, PV plant provides flexibility as well, and that's what I'm going to show you next. As we add more solar to the system, a large amount of solar gets curtailed in order to keep room for regulation results. This was established in a pioneering study that we conducted with a utility, Tampa Electric, TECO in this case. A simulation of dispatch using plexos and the high solar penetrations was carried out by E3A consulting company. It was found that if we treat solar as a flexible resource, as shown on the right-hand side, and use it to provide regulation results, it reduces thermal generation commitment to meet operational needs, and in that case, it also results in reducing annual curtailment of solar by 60% and creates an additional 50% more value for the system in terms of production cost reduction. A DOE-funded follow-up study was carried out which showed that flexible solar can reduce annual system cost in California by 172 million. So the annual cost, that is. So the benefits are indeed real. Next, I would like to talk about IBR standards. For the past 2 years, a large industry-wide working group has been actively involved in establishing common standards for IBR resources for interconnection to the transmission system. A draft standard has been released for balloting purpose with 99% approval from the team. It contains many requirements, as you can see here, including frequency response, reactive power, etc. I will highlight one particular requirement that pertains to frequency response. The capability that's specified in P2800 is shown below the red line here. And it has raised the minimum bar of what kinds of standards we should be looking for. And the TS owner, the transmission system owner, may require additional capability. But at least this defines the minimum capability requirements for IBR resources. One of the capability that's was required or is required by the P2800 standards is fast frequency response capability, which is described next. This response was motivated by the fact that as IBR penetration increases because of wind and solar and traditional synchronous generation proportion decreases, the system inertia will decrease. For example, if a large generator trips offline, then there's a large frequency drop on the system. This is kind of illustrated on the top right picture there, where you can see the frequency drops dramatically, and then during the arresting period, you do usually have the inertia effect that will slow that down. Now, and then it follows with, and it's shown on the bottom right, is primary frequency control, where the governor response of other conventional generation, etc., take place, and they tend to help recover the frequency, followed by secondary and tertiary frequency control. So the P2800 standard postulates that IBR should be capable of providing FFR, or fast frequency response, to counter the impact of low inertia. This chart illustrates what a FFR from a PV plant with reserve would look like. It is observed that the plant increases its output, so let me first show, as the frequency drops, and once it reaches a trigger point, the PV power starts increasing its output, assuming that there is certain reserve maintained by the PV plant for that purposes. And then once the frequency, so in this case you can see it jumps about 27% jump in power within less than 10 seconds. And as the frequency, which is shown on the bottom chart there, goes back to the trigger frequency, basically the PV power goes back to its pre-disturbance normal point. Next, I'm going to summarize some of the key points of my presentation. The capability of a grid solar IBR plant is now well established. It consists of base capability as voltage regulation, power control, right-through behavior, frequency droop, etc. that we discussed. It can also provide reliability services that we talked about, AGC, up regulation, down regulation, frequency regulation, and so on. Once we combine a PV plant with storage and make it into a hybrid plant, it can also provide additional capability, which includes capacity firming, energy shifting, and additional flexibility. However, with IBR resources, we have just scratched the surface. There is considerable research being done to add more capability in IBR that will enable a future digital grid that is affordable, secure, reliable, clean, and resilient. Thank you for your attention. Thank you very much for your attention. I'll be glad to answer any of your questions. You can even email me your questions at the above address. Thank you.